Good day, everyone. My name is Joshua Manzano, and I am presenting our paper entitled Using Boolean Satisfiability Solvers to Help Reduce Cognitive Load and Improve Decision Making when Creating Common Academic Schedules. Our paper focuses on student scheduling, which is defined as assigning students to sections of each course such that they have no schedule conflicts. Many universities employ a method wherein they let the students pick their own courses and create their own schedules. This entails students having to pick from a list of courses and creating their own schedules. This usually leaves them having to deal with picking from a lot of courses and also coordinating it with a lot of peers. This leads to mental stress and high cognitive load, which then impairs their decision making and makes them create poorer quality schedules. Related literature around this problem shows that scheduling tends to be a complex task due to the constraints involved. And due to this complexity, the quality of the final decision, and in this case the schedule, is more likely to be stifled. And bad schedules can affect the grade and performance as well as the motivation of a student. Constraint satisfiability has been proposed as a technique that can be used to solve the student scheduling problem. An example of such technique is the usage of a satisfiability solver, which has been used in course scheduling, employee timetabling, and tournament scheduling. There is an opportunity to integrate a SAT solver in a semi-automated system to tackle the problem of student scheduling. There have been minimal studies in tackling the student scheduling problem, especially with a SAT solver. So our research questions are as follows. First, what impact does the use of a SAT solver-based system have on the decision-making process in schedule creation? Next is, what impact does the use of a SAT solver-based system have on the cognitive load of users? To answer our research questions, we have the following methodology. First, we do need finding to identify the preferences and the necessary design goals needed. Next, we design the system and configure the SAT solver. And next, we evaluate our proposed system to existing methods. For our need finding, we were able to gather 54 respondents, and from these 54, we were able to interview 16 respondents who had unique and unexpected answers. To further understand, we got another set of 5 respondents for contextual inquiry. From this, we were able to create our preference taxonomy, which is used as a basis for a SAT solver. And we had the following design goals, which is first, to improve efficiency, to reduce stress, and to minimize mental load. And thus, our system was designed with these design goals in mind. To evaluate our system, we recruited 7 friend groups with 2 to 4 participants each, for a total of 42 participants. These participants were separated in control group, which were allowed to use any method or system they want, and the experimental group, which used the proposed system. They were tasked to create their schedule individually and to coordinate with others. To measure the different aspects in schedule making, we used multiple metrics for each aspect to ensure that we correctly capture each aspect. For our results, we found that students experience less difficulty when using our proposed system. This can be seen in subjective mental effort questionnaire and the NASA TLX. It is interesting to note that students in the experimental group found that they experience less physical demand than those in the control group, even though the task in general is not really physically demanding. We also found that students were able to decide faster and create their schedules faster. We saw that students experienced slight confusion with the first group task, and this was attributed to the lack of feedback and confusion with how some of the automated features were used. We also found that students experienced less stress. For the user experience, we found that in general, in most aspects in the user experience questionnaire, the proposed system had good and excellent scores, with the exception for perspicuity, which is just above average, which can be attributed to the aforementioned confusion. When asked to pick between schedules created by the control group and the experimental group, we found that students favored schedules created using the proposed system, which is the experimental group. In general, students were also more satisfied and think that their method was more efficient when using the proposed system. For design recommendations when creating a user-centric, semi-automated system for creating personal schedules, we provide the following recommendation. Is to first, provide informative feedback with semi-automation. This is due to the fact that feedback reduces the likelihood of perceived ambiguity and confusion with automated results, and also aids with decision making. Next is to visualize and contextualize content through the use of visualization such as a calendar or weekly view with color highlights, as these can simplify the task of deciding a common schedule. Next is to always strike a balance between automation and autonomy, as too much automation often leads to the user getting confused and actually harms their decision making and their efficiency. For future work, we would like to explore more collaborative features to benchmark against other automation algorithms and to explore course timetabling in tandem with a semi-automated student scheduling system. That is all. Thank you for listening.